Okay, so okay, what's the answer to that? Oh, sorry. I like that one. I meant, what did I mean? No, do I? Here, let's see. Let's try this. Try again. I mean this. If I evaluate directly, what do I get? No limit, right? I get 1 over 0. Okay, so okay, let's get more specific. So what is it really? We can get more. You can't give me an answer, but you can give me a more meaningful answer than no limit. You can't give me an exact answer. You're not going to be able to give me a numerical answer. Okay, so yeah, let's look at the nature of the graph. What is this graph? Let's just throw up a quick sketch of the graph. Okay, so what does this graph look like? What if I take values, like if I were to plug in, for example, a really small positive number, what am I going to get back? Like 0.00001. Oh, sorry, I mean like 1.0001. I'm going to get 1, right, which is what? It's going to be a really small number, right? Okay. In fact, it's even going to be a smaller number, right? Because like 0.1 squared is what? 0.01, right? So if you're less than 1, thanks. If you're less than 1, and if the absolute value of a number is less than 1, and you square it, it actually gets smaller, doesn't it? So would you agree that as as the ant walks backward towards 1, it gets really high, right? As we get far away, though, like if x is 10, well, 10 minus 1 is 9, squared is 80. 1/81 is pretty, right? That's pretty small, isn't it? Right, so what's it going to look like then? It's going to look something like that, right? Okay, what about the other side? What's it going to do? Same thing, isn't it? Yeah, it's going to be the same thing, right? And we know that because if I were to do something like take 0.999 or something like that, well, 0.999 minus 1, yeah, I get a negative small number, but squaring it makes it positive, doesn't it? Right? And so we end up with something like that, right? Okay. Just a quick review topic here for a second. This is just fun to talk about math. How could we get that graph as... What parent graph could we use to get that graph? What parent graph could we get to get a graph of 1 over x minus 1 squared? 1 over x squared, right? And if we did 1 over x squared, we can utilize some symmetry. I just want to kind of, one of the things that helped me a lot, and I had a really good calculus teacher in high school. The guy was very knowledgeable, knew a lot about math. And then in college, of course, he was a really knowledgeable math teacher. Just having him talk about, think out loud like a mathematician really always helped me. If you just kind of, I think gradually, we learn by patterning. And so sometimes I think it's important just to kind of go through stuff, even if it's not calculus stuff, and just talk about how you think about it like a mathematician. And I think gradually you kind of pick up on those patterns. So we could, if we wanted to, we could take a function like, let's call it g of x equals 1 over x squared. That's an easier one to graph, right? all we have to do there, if it's 1 over x squared, if we were able to get this side in the same way that we did before, now we can use symmetry here, right? How come? How could we use symmetry? What kind of symmetry does this have? Do you remember this stuff from... Okay, so there's two kinds of big symmetry that geometric symmetry that we talk about, right? We talk about even symmetry and odd symmetry, right? Remember this stuff? This is pretty important stuff. This is good to know. It saves us a lot of work. What is the definition of even symmetry? So what do? We fold? Is that what you said, or you rotate? Which one is it? Are you gonna? I don't want to put words in your mouth. Yeah, the third down here. Okay, that's odd symmetry. Okay, even symmetry is folding symmetry about the y-axis. Okay, so even symmetry is symmetry where it's going to do something like that, for example. Right? It folds over the y-axis. Here's our test for even symmetry. F of negative x equals f of x. Okay? In other words, the y value I get from negative x is the same as the y value I get from positive x, right? And say it again. Then it's odd, right? So odd symmetry would be like this. That's going to be rotational symmetry, so it's going to look like that. It's rotational symmetry about the origin. And that's f of negative x equals the opposite of f of x. Okay? Does that make sense? And where does the even and odd come from? By the way, the even and odd just comes from if you have a polynomial with only even exponents. By inspection, you can look at it and say it's got even symmetry. Right? So, for example, if I had the polynomial y equals 3x to the 4th plus 2x squared plus 3, what's the power of x associated with the constant 3? 0. Is 0 odd or even? No. It's even, isn't it? It matches the pattern, you know, -4, -2, 0, 2, 4, 6, right? It's even, isn't it? Okay, so this has got even symmetry, so guaranteed that polynomial, without even knowing at all what it looks like, we know it's got to have even symmetry, right? Odd symmetry would be a polynomial, for example, like y equals 3x to the 5th minus 2x. There I've got an x to the 5th and an x to the 1. The exponents are only odd, and so it's going to have rotational symmetry about the origin, guaranteed. Okay, that's where those names come from, right? Well, which one does this have? We could just run a test and see, right? If we plug in negative x, what kind of outcome do we get? Well, that's going to give us 1 over negative x squared, but what is negative x squared equal to? X squared, right? So there we end up with g of negative x equals g of x, so it's guaranteed it has even symmetry, right? So we know it has to have folding symmetry about the y-axis, right? So that's an easy parent graph to get. And then what does, can I go, is everybody, are we done with this page for the moment? If I go back here, well, what did I do? If I started with the parent graph, g of x equals 1 over x squared, how does this transform that parent graph? If I subtract 1 from x, it shifts it right by 1, doesn't it? Yeah. Okay. Does that make sense? Okay, so there's an alternate, consistent way of coming up with a quick sketch of that, right? Okay, but back to the calculus, right? So we can see from the graph that now instead of no limit, we can be a little more descriptive. As the ant approaches 1 from either side, what happens to him? What does he approach? positive infinity, right? Now, that's a different kind of limit. You got to be careful with that. When we say something like infinity, you got to take that with a grain of salt, right? Infinity is not a number, but it does tell us something important. It tells us that it explodes in a positive direction, right? That's not a limit, is it? Because that's not a number value, right? So it really is still no limit, but that's much more descriptive, okay? What about something though if we want to try something like this? Let's change that ever so slightly. Let's take the limit of 1 over x minus 1 as x approaches 1. Okay, now think back to our line of reasoning here that we used before to come up with a sketch of this, right? And just exercise your brains a little bit. And this literally is like pumping iron with your brain to kind of do lots of stuff mentally. Makes you smarter. So what's that going to look like? If we were to transform the parent function 1 over x, what does the graph 1 over x look like? You might remember that. That's one of our common. What's that look like, Lily? So it's got behavior. Okay, so the parent graph, if we take y equals 1 over x, that's a little different, isn't it? It's going to have that behavior, but then that behavior, right? Everybody agree? And it's going to get moved to the right. Yeah. So this time we don't get as satisfying an answer, do we? Right? We can't say infinity because only one of the ants goes to infinity, the other one goes to negative infinity, right? So can we come up with maybe a better way of dealing with this? What if we were to take one-sided limits instead? What if we said, what's the limit of 1 over x minus 1 as x approaches 1 from the right? What's that going to be? Positive infinity, okay? Compared to the limit of 1 over x minus 1 as x approaches 1 from the left, where's that ant going? Negative infinity. Okay. So we've based this all on the graph though, right? What if it's not so easy to draw a graph? And it won't always be, right? Is there another approach we could take to get the same answers? There is. As I approach 1 from the right, and you might want to put this in your notes, because this is kind of my own little thing. I mean, it's the notation I've always just used for myself, but it works pretty well. And so I'd encourage you to use this also. If we approach 1 from the right, what does the result look like here, right? If I approach 1, on the bottom I'm getting a value of 0, right? Everybody agree? I'm approaching 0, but I never get there, right? What's the sign of that number going to be? If I'm approaching 1 from values bigger than 1, I've got something like 1 plus is how I would describe this, minus 1. What's that leave you with? It leaves you with a small positive number, right? The way I always notate that is I'm going to put a plus up there, meaning which is real similar to our limit notation, right? So that means I've got 1 over a small positive number. Well, what's 1 over a small positive number? 1 over a small number is explosive, right? That approaches infinity. So this part right here is telling me that I've got infinite behavior, and that part right there, if I look at the signs of the two, I've got a positive over a positive, right? So that's a positive 1, right? That tells me that it's a positive infinity. See how we're doing that? Okay, on the bottom, we've got the same kind of behavior. We know that if I'm now approaching 1 from the left, that's from values of 1 slightly less than 1, right? So 1 minus 1 is what? Small negative, right? So we could write that as 1 over 0 minus. See what I'm saying? Okay? So what's the behavior look like then? Well, we know that a 1 over 0 is infinite. Now let's look at the sign of the quotient. I've got a positive number divided by a small negative. So I end up with negative infinity. Do you see that? So we don't have to rely on the graph. Right? We can just think about this in terms of the behavior of the quotient as we approach but never get to that number. Okay, let's look at another example. What if what about something like, well, so before we do another example, let's attach some rigor to this idea. So we got this informal definition. Remember, if we go back to the definition of a limit, right, kind of the more formal definition of a limit, the alpha or the epsilon delta definition, remember what that was all about. We just said that as long as we can get as close as we need to our limit by shrinking the neighborhood of values around C, then it works as a limit, right? Does that make sense? As long as there's a connection, right? Well, this is a different kind of a situation here. This time we're not approaching a value. We've got this infinite behavior, but how could we formalize this in a similar way? As long as getting us closer and closer and closer to C, so shrinking the neighborhood of values around C, is going to just continually drive us up further and further and further up the function without limit, then it makes sense for us to say that the limit of the function as x approaches C is infinite, right? Now that wouldn't work if, as we got closer at some point, the function dipped down again or something. Then that doesn't work, right? As long as the function is continually going up and up and up, then we could still say that we could formalize this definition, right? And so take a look at this. We're not going to do a lot of, part of your assignment, the implied assignment here, is that you're going to read this definition about 10 times, and you're going to kind of hurt your brain to think about it a little bit. I just want you to do that. I'm not going to give you a bunch of problems about the formal definition of an infinite limit, but just understand that we can attach the same kind of formal notation to it, and it makes sense, okay? All right, so now what? So we've got this idea of an infinite limit. Let's let me pull one out of the book. I thought I had one on my example list, but I don't. Yeah, this is a good one. Let's look at, okay, I don't know if it's not some fun. Okay, relativistic mass. Yeah, okay. So some weird things happen when you increase your speed. Okay, this is relativistic physics. Einstein showed us this. And this isn't stuff that you would ever witness in everyday life, but when you start to get an object that moves at speeds that are much higher than normal speeds. The speed of light is fast. The speed of light is, they know what it is. The fastest thing ever. There you go. That's true. Anybody know what the speed of light is, though? It's an actual in terms of like units of speed. it's 180, one way of saying it, it's 186,000 miles per second. Yeah, that's fast. 186,000 miles per second. So circumference of the Earth, that's going to be roughly about 7.5 times around the Earth every second. That's how fast light travels. Okay, that's pretty fast. To get from the sun to us, it takes about how long? Yeah, I've heard 8, I've heard 9, I don't know which one it is exactly, something like that. But it is a measurable amount of time. But it goes pretty fast. So nothing we have is even remotely on that scale, right? I mean, the very fastest things we can do physically are so far below that we never really witness this, unless we're talking about the types of velocities we can achieve for very, very small particles and accelerators. Like, for example, if you were to slam a massive particle into a piece of lead foil and create a cascading collision of subatomic particles, some of those would be positrons. If you took those positrons and which have the mass of an electron, if you took those positrons and you accelerated them down the Stanford linear accelerator, and you injected enough energy into that to accelerate that little packet of just a handful of particles, so that it was the equivalent of the entire energy use of the Bay Area for just a quick little second, which is what they do. I mean, not even a second, just a very small fraction of a second. You could get those up to within about 3 trillionths of a percent of the speed of light, and you'd notice some bizarre things happening. Some very bizarre things would happen. If you were to look on a macroscopic scale, if you took something like a car, and I were to drive a car down this lane right here close to the speed of light, you would notice that physically its length along the direction of travel would contract a lot. It's called Lorentz contraction. It really happens. You would notice that time, if the person were holding up a big clock as they were driving by, you would notice that their clock would be running much more slowly, called time dilation. You would also see that the mass of the car would increase massively, like the mass of these particles when they get traveling down slack, and we can measure this. Their momentum, which is proportional to their mass, increases much more than you would expect it to using classical physics. In fact, it exactly follows this model. The relativistic mass equals the rest mass divided by the gamma factor, which is the square root of 1 minus v squared over c squared. What's c? Speed of light. What's v? Yeah, the velocity or the speed of whatever you're measuring, right? So let's see what happens here. Let's take a limit, because we can't ever get to the speed of light, right? No object with mass could ever go the speed of light. It would require an infinite amount of energy, and that's not possible in our universe. So what happens if we take a limit then? The limit of the relativistic mass as v approaches c, and there has to be a direction associated with that. V approaches c from which side? So if I were to graph this, what would the graph look like? And I want you to think about, when you start to think about graphs, you always want to think about graphs in whatever the space of the dimensions would dictate, right? So if we were to graph this thing, we're graphing mass as a function of what? Velocity. Okay? So as we increase velocity, there's going to be some upper limit at c, right? So in what direction is the velocity approaching c, from the left or the right? Has to be from the left, doesn't it? Right? Because you can't ever get to the velocity of light, let alone past it, right? Does that make sense? So we have to have a direction associated with it, and the direction is minus. That only really makes sense if you think about it in terms of the graph, though. You see what I'm saying? Okay. All right, so what do we get then? So we get the limit of the rest mass, which is a constant for some object, right, divided by the square root of 1 minus v squared over c squared as v approaches c from the left. Okay, so then if we evaluate this directly, what's that look like? If v is approaching c from the left, okay, I'm going to get something slightly smaller than c divided by c. What might you call that? What's it going to look like? C negative, okay. But what's C negative divided by C? C minus divided by C would be what? Say it again, Richard. Well, meaning it's going to be something slightly less than 1, right? Does that make sense? So when I say something like 1 minus, does that mean that's the sign of 1? No, it's positive, but it means it's a number slightly less than 1. You get that? So then what's that look like if I square that? If a number slightly less than 1 gets squared? Okay, right, so I can do it up here, I guess. I'm going to get m naught over the square root of 1 minus, now think about that again. If I have a number slightly less than 1 and I square it, like what is 0.9 squared? 0.081, isn't it, right? So it's a number that's also slightly less than 1, right? Does that make sense? So I could just call that 1 minus, right? Everybody agree? Like 0.99 squared would be even closer to 1 if I squared, right? So I end up with 1 minus 1 minus. And what's that equal to? A very small positive, right? Good, so that's equal to m naught divided by the square root of 0 plus. And what's the square root of a very small positive number? A very small positive number, right? So I get m naught over 0 plus. Well, rest mass is always positive, right? So what's my answer look like? I've got a positive number divided by a vanishingly small positive number is what? Okay, that tells us something really profound, right? What's that tell us that the mass of an object approaches as its speed approaches the speed of light? Infinite, right? It approaches infinity, which tells us an awful lot, which tells us why it requires so much energy to get something close to the speed of light, because you can't push something with infinite mass, right? Does that make sense? And so you could kind of think about this. It gives you a little insight into physics here. The energy that you're using to accelerate an object as it gets close to the speed of light, it starts off being exclusively invested in an increase in speed. But after a while, as you push this thing harder and harder, your push instead gets translated into an increase in mass, right? That's how the energy is stored then, is the increased mass of the object, which increases the momentum. Does that make sense? Okay? All right. So kind of the interesting application of that.
Go back to that.
What's that? Oh, go back? Yeah. Yeah.
Hello.
Hey. There's more. Okay. Let me go back first. There you go. All right. Siler's not here. Okay. Everybody else is. Okay. All right. So we done with this? Everything. I'll put this up on the notes too. All right. So next step then. So what could we say about, I mean, I already let the cat out of the bag yesterday, but if we want to kind of look at a problem like this, okay, and we want to take a limit, well, and I want to know, it's not even bother, I'm not going to say anything about a limit yet. If I want to know where this function has asymptotes as opposed to holes, I actually kind of already gave you, like I say, I kind of let the cat out of the bag here. You kind of could probably answer this now, or before even today. But how would I go about finding the places where it has asymptotes, vertical asymptotes as compared to holes? Well, what I probably have to do to the function first? Okay, let's factor it. Good. So what's the top factor into? Over x plus 2, x minus 2. Good, right? Everybody agree? Okay, so based on that, could you tell me, I mean, and you can already tell me this. Today, if we add anything to this, it's just going to be that maybe we can understand why we get what we get. Why these answers are the answers. Where is this function going to have a hole? At x equals 2. How come? Okay, good, good. Because that's where we have indeterminacy, right? Because if I say, if I evaluate the function at 2, I get 0 over 0, right? So that means it's got a hole at x equals 2. Okay? F of x has a vertical asymptote at x equals what? Where? What do you think? Yes, sir. At 2? Negative 2, right? At negative 2, because f of negative 2 equals a number, what do we get? Doesn't even really matter, but we get 2 times negative 4, so negative 8 over 0, right? So we know it's a vertical asymptote. What could we add to that picture today? Because a vertical asymptote could be multiple things, right? We could, though, now we can see, you see what I'm saying? If I say it has a vertical asymptote at negative 2, what could that be? Well, it could be that, it could be that, it could be that, or it could be that, right? How would we know which one? Say it again. Go ahead, say it louder. Okay, well, we could do the even odd test. Sure, we could probably try to approach this with symmetry, but could we leverage this new idea that we had of one-sided limits, right? See what I'm saying? So if we want to know what really is, what kind of a vertical asymptote is that, we could take this function. We could take this function and take what kind of limits. If we know that our vertical asymptote is at negative 2, approach negative 2 from the left and the right and just see what happens, right? Okay, so let's practice that once. So what is the limit of this guy? Well, for one thing, we could just cancel those out algebraically, right? And we'll see that in the math here. I'm going to leave them in there, but I want you to see why you could effectively just cancel those out. As x approaches negative 2 from the left, how about? What's that going to give us? What's going to be the contribution of each factor? What's going to be the sign of that guy? If I approach negative 2 from either direction, what am I getting there? Positive 2. Do I care that it's a 2? No, I don't care. I'm just going to do that. It's a positive factor. Seriously, that's how I think you have to do it. You don't need to waste time figuring out what the actual value is. Here it's easy to do, but sometimes it may not be, right? We just know it's positive. What about this one? Negative. That's all I need to know, right? On the bottom, I'm going to get this guy right here is going to be negative, right? So now you can see why we could have just canceled those. Do you agree? But we'll leave them in there, it's fine. What about this one? That's the important one, isn't it? What's going to be the behavior of that as I approach negative 2 from the left? So that's going to be a number like, and this helps, like negative what? 2.1, right? So negative 2.1 plus 2 is negative 0.1. If we just get closer, it's just 0 minus, isn't it? It's going to be a small negative number. Okay, so what do we get then? How do we interpret this? I've got a 0 on the bottom, but not the top. So that tells me I'm getting infinite behavior. Now I just have to reckon the sign, right? We'll look at all these 4 factors and see what the sign contribution is. If I have a quotient of 4 factors and I have an odd number of negatives, what's the overall sign? Negative. So whether I include these or not, I can see I'm going to have an odd number of negatives, right? Okay, that's kind of a cool little trick, isn't it? Right, forgetting that stuff. Let's try the other side then. So if we do the same thing. And this time, let's be smart about it. And let's just cancel those, make life easier, right? Now, as x approaches negative 2 from the right, what's that going to give me? Positive, right? That's not going to change. The only thing that changes is this guy. What if I'm approaching negative 2 from the right? That's a decimal like what? Negative 1.99 or something like that, right? So plus 2 is going to give us a small positive, isn't it, right? So we end up with infinite because the 0's on the bottom, and positive over positive is positive, right? So now we know what that asymptote actually even did. As we approached from the left, it went down. Approached from the right, it went up. So it was a split asymptote. Okay? Make sense? All right. How much time we got?
5 minutes.
5 minutes? Yeah, we got through a lot of stuff. That's good. Okay, I'll leave you with, here's what I'll leave you with for today. Because this is another, I'm trying, whenever I can, I try to work in a little important review. So what if we want to figure out, what if we've got something like f of x equals x squared minus 4 over x cubed plus 2x squared plus x plus 2. Okay, and I want to know, same question as before, I want to know what are the nature of all of the discontinuities. So where do we have holes and where do we have vertical asymptotes? What would our strategy be again? Okay, factor the bottom. Do you know how to factor that denominator? By grouping. Yeah, you would factor it by grouping. Okay. But what if it were, let's just say hypothetically. Well, go ahead and I'll let you just work on that. I'll throw a different one at you later. Because we can use some strategy here that even if we couldn't factor the bottom easily, there still would be an approach we could take. Okay, real quick, you guys were able to find this intermediate value theorem assignment? Okay. And it makes sense? Oh, yeah. Okay, let's look at the last one. This guy. Okay, so this one, oh, you know what I needed to do on that? Darn it, anyway. Here, let me do one thing to that. If you want to refresh that one, you'll have this I want to give you the ability to attach stuff if you want to. Make that big. And I'll allow you the ability to to allow attachments. So now if you go to this thing, it'll look like this, hopefully. So down here you can drag and drop stuff. So if you want to do this, in other words, you can use, if you open up this editor, right, this text editor, clicking on that gives you access to all the stuff you'd normally have in Wirus and algebra, like well, you guys didn't have any algebra too, but all my Moodle questions. So this is a really robust editor. So that gives you a lot of stuff to do. If you'd rather just do this on paper and then just take a picture and attach it, do that. That's fine. I don't care. Or do it on whatever you want to do it on. If you want to use it on, if you want to use Word and you want to use some fancy algebra editor, that's fine. But all I want to do here is, you don't have to do a lot of math on this, honestly. You could probably just talk me through it too. Well, that's supposed to be capital V too. I don't know why it says that. Pretend that's capital V. I'll change it. So I want you to just describe to me how you know for sure that guaranteed there has to be, that's supposed to be a number. I screwed this thing up, darn it. Okay, I'll fix it. That should pop up a number. It's going to say something like 750, right? Cubic centimeters. So that one's messed up. Whoops. I want you just to walk me through that and just defend why there has to be at least one sphere with that volume. Okay, so go back to that in about 5 minutes and it'll be fixed. Or later, if you'd rather do it later.